Should I start? Okay. Okay. So we have seen how this decomposition theorem applies to the example of graphs. It gives a graph approximation on which some algorithms can be run in time independent of the number of vertices. How it applies to settings like or more general than Fourier analysis, in which the structure functions are characters or low degree polynomials. Now I want to show how this statement applies to the setting where we have probability distributions rescaled and the structure functions are efficiently computable functions. Well, it's not even an application, it's more an illustration of what the result gives. So let's say that D is a probability distribution and let's say it has very high entropy. So for some delta all probabilities are at most 1 over delta times the smallest possible. Now, use as our function g this rescaling of D. So now it's between 0 and 1. And use f to be set of all functions computable, say by within some small complexity measure, say by circuits of size at most f. So we apply the theorem and we get this function h, which is going to be between 0 and 1. Now h is computable by a circuit of size, well, we also fix an epsilon. So in order to compute h, we need to compute the functions f1 through fk, of which there are 1 over epsilon square each of complexity s. And then we need to compute the combining function. So the proof was very general, so it's not clear that this combining function has any structure other than being kind of a collection of 2 to the 1 over epsilon square values that says what's the average of g in each of those places. Okay. And now consider the distribution M so this is a distribution because the sum of the values of h is the same as the sum of the values of g. So after the rescaling, it will sum to 1. It's non-negative. It has also the same very high entropy. So the value of the probability of every element is at most 1 over delta times 2 then. So then we have this pseudo-randomness condition that the inner product of g minus h with f is small. And now when we look at that way of characterizing indistinguishability and the scaling that we are using, this is saying that the expectation of M under our original distribution is the same as the expectation of F under this distribution M. So maybe we lose a factor of delta. So this is when we have a completely arbitrary distribution, as long as it's a high entropy distribution, it is possible to find another distribution which is indistinguishable. I called M to say it's a model of the original distribution, and such that if we want to know the probability of an element under this new distribution, that's rather efficiently computable. So this is that every high entropy distribution has an efficiently computable model. However, there are some applications in complexity in cryptography where one wants to model distributions by efficiently computable ones, but usually with a very small parameter epsilon, something like inverse polynomial in the input length n. So then this would cause the circuit to blow up to more than exponential size, and that makes the result in that setting vacuous because anything can be computed inside pseudo n by circuits. So this also suggests that for this kind of computer science setting, one would like a version of this theorem where this condition is true because that's necessary to make M a distribution. This condition is true because it gives the pseudo-randomness, but H be not only a function of a small collection of functions from F, but also a simple composition of a few functions from F. So with this motivation, give a third version of this decomposition result. So this is another weak regularity lemma. But with efficient composition. So this appeared in joint work with Masoud Madour, Tulsiani, and Salil Badam. Yeah, maybe I shouldn't. Okay. So let's call it decomposition. Yeah. So also the one up there, maybe you should call it decomposition, not regularity. All right, so it under the same conditions. So we're given some function g, say it's non-negative, some functions f. And now an advantage of this argument would be that the f need not be Boolean. And some epsilon and some collection of sorry. F is some collection of functions of this form. We're given G, the collection, and epsilon. Then there are so now our approximation will be a summation of Fi But okay, let's make this much. But truncated, so that if the summation is more than 1, it's 1, and if it's less than -1, it's -1. So I guess I could write I don't know if that's right. That's the simplest way of writing it. But it just means this summation, if it's too big, it's 1. If it's too small, it's -1. Such that okay, k is at most 1 over epsilon squared as before. And we have the pseudo-randomness condition, or the indistinguishability condition. So it's a bit the best of the two worlds, because we get a simple expression that a circuit can evaluate in linear time, just a sum and then the truncation. But we also get H to be a bounded function of the same average as G. Yeah, I don't know if that matters in any case, but it's true. Actually, in fact, all the coefficients are at most epsilon. True. Okay, so let me show you the algorithm. It's basically the same algorithm for the very first case I showed. So we start with a all-zero approximation. But we keep two functions. So while there is a counterexample, so this function S for sum behaves like the same approximation that we had before, but our H is a truncation of S. So we run the same algorithm that we did for the unbounded case, but at every step, what we use as approximation is not the raw sum, but the truncated sum. And then what we show in our analysis is that the norm square of G minus H plus 2 this quantity decreases by epsilon square at each step. And when we get started, this is at most 1, and this is 0 because H and S are the same. So this extra term in the potential function seems necessary because there are steps in which maybe actually H doesn't change, but maybe what's happening is that S is getting less overflow somewhere. So this is the right potential function to look at. Okay. So applied to this setting, this gives us this efficient approximation of functions where there is no term exponential in epsilon. So potentially, this approximation can be cryptographically, where is it? Here, this approximation can be cryptographically strong. Okay. Now, I've been calling all those decomposition results weak results. And so the weakness is in the quality of the approximation. So what we are getting in our approximation is that there is an error of epsilon in this normalization. And we have an approximator that has complexity k, where k is quadratic in epsilon. So somehow the complexity of the approximator is larger than 1 over epsilon, where epsilon is our approximation parameter. So if we think of it in the case of graphs, we have a partition into 2 to the k blocks, so that our approximating graph looks like a combination of complete bipartite graphs between the blocks. So there are going to be 2 to the k such blocks, and the approximation is epsilon. So that means that if I look at any 2 of those blocks and just focus on that part of the graph, I have no approximation guarantee, because the approximation is way larger than the relative size of those blocks. So in the semi-ready regularity lemma, one gets an approximating graph where, in some sense, the approximation holds even relative to the small blocks, although just for most of the pairs of blocks. Now, the way it's stated, it doesn't. One really needs to talk about vertices and edges. It doesn't generalize neatly to this setting where we are just looking at arbitrary functions. But there is, in fact, an even stronger version, just proved by Tao and by Alon and others independently, which has a general setting where we don't need to talk about graphs. So I'll state and prove this strong version and see some applications. So now we get a strong decomposition theorem. In this abstract form, it's due to tau. So we have, again, a finite space, a bounded function. Here, maybe we want it to be 0, 1. You can always renormalize 0, 1, minus 1, 1, whichever works better in the argument. We have some collection of functions. Now, again, the argument is easy only if the functions are Boolean. It gets a bit more messy if they are arbitrary and need to be discretized. We have some parameter epsilon. And now what's new is that there is also some other input to the algorithm, which is some arbitrary function. So this is what's given. All right, then. What are the arguments of capital F? Yeah, what are the arguments of capital F? Well, let's say it maps integers to integers. I wanted to get to it later. Okay. So then there is there is a three-piece decomposition of G. So then we can write G as three pieces. Such that H1 is low complexity. So H1 is the conditional expectation of G on some collection of functions. And let's say there are k such functions. Where k, okay, so the fi belong to f, and k is something that depends just on epsilon and f. So H1 is low complexity. H2 is pseudo-random. So the inner product of H2 with any f, but it's pseudo-random with with sort of with an upper bound which is whatever we want. So at the beginning we could have specified, okay, the approximation is going to come out depending on k functions. I don't know what k is, it's whatever the algorithm will give me. But if the approximation is going to have k functions, I want the additive error to have a pseudo-randomness 1 over 2 to the k. Or maybe I want it to be 1 over 2 to the 2 to the k. So if there was no H3, basically this is just G minus H1. So I'm saying that my low complexity approximation is indistinguishable from G by some parameter which can be much smaller than the typical size of the blocks that the sigma algebra partitions X into. So without an H3, this statement is false, but what I'm also going to add is an extra piece of small L2 norm. So the way it's different from the others is the fact that we add, so before we just had low complexity plus nearly orthogonal part. Now we add one more part which is bounded. And the advantage is that we can get the quality of the approximation to be really high compared to the complexity of the approximation. What? You want to?
No, the quality is not H3. Why is it the quality of approximation is not H3? Or is it H3?
The quality of the approximation is both H2 and H3. So the fact is that in general, when we talk about approximation, actually we might be talking about unapproximable functions. Like imagine that G is a random function and curly f is linear size circuits. Right? So we're really talking more about indistinguishability. So potentially, like in all constructions, the approximation and the original function are very different. It's just that the difference is not observable by efficient functions. So here we are adding something that is sort of unconditionally small. It's small in L2. And what we gain is that the computational quality of the approximation becomes negligible in the complexity of the approximation. Unfortunately, this is not applicable to the setting where G is a scale distribution, because the addition of this term disturbs the possibility of H1 being itself a distribution. Not to mention this k will be astronomically large in 1 over epsilon. So what does it say about graphs? So a typical statement that one wants to prove from a theorem of this form for graphs is the triangle removal lemma. So it's an example of the application of this theorem. So the triangle removal lemma says that informally, if G is a graph that has little o of V cube triangles, then all triangles can be broken by removing a little of V square edges. Or counterpositively, if you need to remove a constant times V square edges in order to make the graph triangle free, then the total number of triangles in the graph must be some other constant times V cube. This is powerful enough to give a proof of Roth's theorem, of Semedi's theorem for arithmetic progressions of length 3. All right, so this is what I said before is the quantitative statement that so for every delta there exists an epsilon such that if one has to remove more than delta V square edges to make G triangle free, then G has more than epsilon and V cube triangles. So the way one proves this theorem from the lemma is to apply this decomposition to G, seen again as a Boolean function that maps a pair of vertices to 1 if it's an edge or 0 if it's not an edge. So this will give us this, and we will do the decomposition by using characteristic functions of cuts as our structure functions. Right, so suppose you're given G. Yes. So I'll take G to be one if it's an edge, 0 if it isn't. So I'll take F to be all those characteristic functions of cuts as we were doing before. So I'll use some parameter epsilon that will depend on that delta. And I think something exponential in k maybe.
1 over f already?
Yes. So I have something like 2 to the k. Yeah. So then what happens, we get these functions, h1, h2, h3. So I'm going to take my graph h to be the one where the weight of an edge is h1 plus h2. No. Just h1. So in H, the functions that define the conditional expectation are partitioning the set of vertices into at most 2 to the k blocks, such that the presence of an edge with some weight between blocks depends only on the identity of the blocks. Now, I'm going to look at whether there are any 3 blocks that have a reasonable amount of edge weights between them. So if there aren't, it means that if I remove from G all the edges that here had low weight, I'm breaking all triangles, and those will not be many edges. And if there is, I can argue that there is a cubic number of triangles in G just between vertices of these 3 blocks. Because I'm able to say something like, okay, I have a vertex here in and it has large degree in H, so in most cases it must correspond to a large degree vertex in G. Because if most vertices in H have different degree than in G, we can find some cut distinguisher. And then it must also have many vertices that are neighbors here. Now, this is a reason. So now those are sets of vertices of size roughly 1 over 2 to the k, and that's large compared to the approximation that you are getting, because our approximation is better than 1 over 2 to the k. So if here we see a large edge weight between these blocks, it means that here we're going to find a lot of actual edges between those vertices, and each of them will be a triangle. So then we repeat it for every vertex in this block, and each of them is giving us a quadratic number of triangles. Yeah. Very roughly, there is some calculation to do, but that's how it goes. Notice that if we were using the previous type of regularity lemma, and we find a triangle in the approximating graph, those triangle is made of blocks of vertices of density much less than epsilon, where epsilon is the approximation that we get. It's entirely possible that we see this triangle in H, and when we look in G, that's completely empty of edges, because the degree of precision is much worse than the coarseness of the partition. However, thanks to this, the fact that we can control the approximation that we get, we are able to say that a triangle in the approximating graph corresponds to a triangle in the original graph. Right. So how do we prove this strong theorem? This is an interesting variant on those iterative arguments. right, so we're going to start with two lists, both empty. Then we're going to say, well, we'll see what kind of so then we're going to look at whether the second list is giving us the desired approximation. So if there exists an f such that the conditional expectation with respect to the second list is not a good approximation. When it is, we'll see it then, we are done. When it's not, we add f to our current approximation. Then we check how out of sync the two. So at the beginning, this is just nothing. GL is constant everywhere. But then, as we find counterexamples, we keep getting this partition better, while the other ones stay just constant everywhere. Then we check when those two are going to get completely out of sync. When they do, so if they get too far, then we reset them to the same value, the final one. And then when we are done, we use the coarse approximation as H1 and how do you call that?
Luca,
yeah.
These are both epsilons. Is it starting with one of them?
Thanks. You're right. So this is 1 over f of L epsilon. Thanks. Okay. Well, first let's see that if this algorithm terminates, it's giving us what we want. Okay? So what happens when the algorithm terminates? Well, then G of, let's see. Ah, no, I think it was right. So when it terminates, H1 is just a second, it's G minus G. Okay, sorry. Let me just get all three so then it's clear. Okay. So H2 is the one that has to be small, so it has to be G minus GL prime. And H3 is the one that is small in norm, and so it's going to be GL prime minus GL. Okay. Do they add up to G? Yes. Okay. Okay, so they add up to G. H1 has low complexity because, well, H1 has some complexity, whatever is the size of L. H2 is pseudorandom with parameters 1 over f of the size of L, as we wanted. And H3 is small in L2. So the point is whether this algorithm terminates and how soon.
You set L to L prime, and then you set H3 to GL prime minus GL. But at that point, aren't they the same things, GL prime and GL?
No, because that only happens when, it could be, but it only happens when after you execute this instruction, you never keep going through the while cycle again. So the way a typical run of the algorithm is the following. You start off with GL and GL prime being the average of G everywhere. Then you find some function that creates a counterexample. So then GL stays constant everywhere, and GL prime starts being the conditional expectation over this function. Then you find more and more functions that give you discrepancy, and you keep adding them to the conditional expectation. At some point, you get an approximation that is noticeably far away from the constant everywhere. At that point, GL is reset to being whatever was the current approximation. Now, maybe that's good, but probably not. So you keep finding more counterexamples, and now you keep refining the L prime approximation, where the L approximation is whatever you had reset it before going on. Now, maybe you end at some point, or maybe you keep going and again get epsilon away from where you had reset GL, and now you reset GL again, and then you keep going. So the fact is that there are kind of big steps and small steps. GL prime changes in small steps, because when you add f, possibly the discrepancy is only this much. GL changes in big steps, because when you change it, it's because it had gotten far away by this much. Okay. And so this is basically the analysis, that it's true that GL prime changes in small steps, but it changes in steps. So every time you do this, you are adding this much squared to the L2 norm squared of GL, but the same analysis we did before. And just a sec. So the change is always orthogonal to where you were before. So every time you add this to L prime, you get this far away from where you were before. So after this many steps squared, or times epsilon squared, you satisfy this condition. So there is always a finite number of steps between after which this condition happens. But when this condition happens, you are increasing the L2 of GL by epsilon squared. This can happen at most 1 or epsilon squared times. Okay? So that's the analysis. This converges in finite time. That depends only on big F and epsilon. And the shape of this dependency is whatever is the function f applied to itself 1 over epsilon squared times, with another square in the middle, but roughly. So if f is an exponential, what you get is a tower of exponential whose height is 1 over epsilon squared. Russell, you wanted to say something?
So one thing I didn't understand going back is that you really, in advance, you don't know what pseudorandomness you'll get or what complexity you'll get.
Yes.
You just know a relationship that the
That's right.
pseudorandomness is better than the complexity.
That's absolutely true. So what you specify as input to the algorithm is, you're going to get me some low complexity approximation satisfying some pseudorandomness condition. And whatever is the complexity and whatever is the pseudorandomness, I want the pseudorandomness to be exponentially small in the complexity. Now, give me something. And the algorithm will churn, and maybe we'll find the hyper-exponential complexity, but even more hyper-exponentially small pseudorandomness. Okay. Good. Now, what I want to talk about in the last half hour is sort of analogs of those results where so each of the applications that I described, the arbitrary object that we were trying to approximate was also completely arbitrary. It had some kind of density. Like when we apply this result to graphs, we always get some error in terms of the number of edges that we count between cuts of the form epsilon times v squared, where v is the number of edges. So if the graph is very sparse, the completely empty graph is an excellent approximation. So the result is kind of vacuous if the graph is not dense. And when we apply that to distributions in I don't know if it's still written somewhere, but probably not. But we needed our distribution to a very high entropy because whatever was the entropy deficiency of the distribution was coming as an extra error in our computation. And for very sparse distributions, there was no good result to be extracted from the theorem. So it would certainly be very useful to have a regularity type lemmas for sparse graphs. But in full generality, they cannot be true. So for example, so let's talk about sparse decomposition results. So this sentence is in general impossible because let's look at a cycle. By which I mean, if this has some set of vertices, it will be the function mapping pair of vertices into 0, 1. Maybe those vertices are 1 through n. So G takes n squared inputs, but it's true only for n inputs. So it's very sparse function. Well, this graph cannot have any regular approximation. So it's not possible to find a graph H in which there is some constant number of blocks of vertices and then complete weighted bipartite graph between the blocks with the property that every cut in this graph is cut by approximately the same number of edges as any cut in this graph. I mean, yes, if you take approximate to mean up to epsilon times n squared, because then you can take H to be empty. But if you normalize by the actual number of edges, you cannot get a regular partition of this form. And I guess one reason is that if you take like a very sparse cut like this, so this will correspond to some cut in the regular partition. And you've got to get the same number of edges approximately coming out. So you're going to see very few edges coming out of your set, or sort of edges whose total weight add up to 2 plus minus epsilon. But then look at the other cut in which instead of picking this interval, you pick every other vertex of this interval. Now there are n over 4 edges coming out of it here. But then looking at it here, the number of when you count the number of edges coming out, since there are no edges inside the blocks of the partition, there are only between partitions, can only be less than they were before. That before you were summing between partitions that were affected from the cut and partitions that weren't, some ratio of how many were affected. And now that you get this, you get more or less the same value or less, but actually this jumped from 2 to n over 4. And a kind of technical reason why the proof fails in the sparse case is that we were looking at so in the sparse case, we are interested in normalizing not by the total number of possible inputs, but by sort of what's the density of the non-zero values. So if we wanted to get if you have some graph G that is that doesn't really have v square edges, but has I don't know, some really small number times v square edges, what makes a bit more sense as a normalization is that we look at G as a function whose value is either 0 or 1 over e. So that now its expectation is a constant. In fact, it's 1. You could choose a different constant, but in order of magnitude, you sort of want to make G in the places where it's not 0 really huge so that its average is 1. Then, when you compute its inner product with cuts, what you're getting is the fraction of real edges of G that cross the cut, not the fraction of v square edges that cross the cut. And now you have a better normalization. Now, when you do the analysis, so the analysis keeps working. So you can argue that GL square increases by epsilon square at each step. But the fact is that you cannot say anymore, well, when we get to 1, we must have stopped. We could be going all the way up to 1 over e, or 1 over e squared. However, if G, instead of being some arbitrary sparse graph, was a kind of nice sparse graph in which, say, GL is, I don't know, at most 10 for all L of size up to, I don't know, 100 over epsilon square. Now we are in business again, because you can say, okay, I'll do the iterative, say for the weak decomposition theorem. I'll do the proof that I was doing before. I look for counterexamples starting from the constant approximation. And every time I find a counterexample, I add it to my conditional expectation. Now, every time my norm square of the approximation increases by epsilon square. However, even though G has this wild behavior, its conditional expectation is quite flat. And so this norm square can never be more than 100. And so I don't need more than 100 over epsilon square steps. So what does it mean that the L infinity of GL is at most 10? And so why this fails for the cycle? So this is saying that so what is GL? We have some list of cuts, and then we have a new weighted graph in which the weight of an edge depends only on which of the sets in the various cuts that edge belongs to. So it means that we have some partition. So the sigma algebra generated by the functions in L. And now we are looking at, so then GL is the graph where the weight of an edge is just the expectation of it's sort of the probability of finding an edge of G when picking a random vertex here and a random vertex here, but rescaled by the density of the edges of G. Right? So this is saying, okay, maybe G, for computers, let's say G as D times n edges. So that means that the way we rescale the little g, it has values that are either 1 or roughly n over d. I guess n over 2d. Okay. And now I say I have some set A and I have some set B. The value of GL here is the conditional expectation of G, given that we're looking at a vertex in A and a vertex in B. So it's so this is saying, so if this is at most 10, what this is saying is that, so this would be the actual probability of finding an edge between A and B if we were looking at a random graph of the same density. If this is at most 10, what it's saying is that when we look at two sets of vertices, the number of edges that we see between them deviates from how many we would see if we had a random graph of the same density by a multiplicative factor of at most 10. So the cycle totally doesn't have this property because it's a because it's bipartite, and so
somehow it makes more sense. Somehow, because no graph has this property, the A and B are singletons.
if A and B are singleton, no, this is an upper bound. I want to say that.
Yes, so you want to say that this is true, this is
Oh.
less than 10, for the sets A and B that have some constant, that are constant fractions of the graph. But since L divides things into a constant number of regions, you can not worry about the ones that are very small.
But you took infinity loop.
Yeah, so I guess this is too much to hope for. So maybe it's, but it's just enough that the L2 square is small.
So then you don't care about it.
Yeah, so I guess you're right. If they're small, they're absorbed, and if they're large, this might be true.
I think the cycle works fine.
The cycle works fine.
No, but you want some graphs to do have this property.
If a graph has this property, then I can do the proof of the regularity lemma.
I think just with infinity, no graph had this property, but now some graphs.
Okay. Now, if I have a very good sparse expander, then for large sets, this property will be true not just with 10, but actually with a constant arbitrarily close to 1. And then I can see from the normalization that if I start from a very strong expander, and then I take arbitrarily 1/10 of its vertices, I will end up with a graph that satisfies this property with the constant. Sorry, 1/10 of its edges. Arbitrarily 1/10 of its edges, then this property will be true. So it is possible to prove a version of any of those regularity lemmas, not for any arbitrary sparse graph, but at least for any sparse graph that can be put inside a very strong expander, provided that the fraction of edges of the expander that our graph is made of is large compared to how strong was the expansion of the graph. Now I'll
Being dense in the complete graph is a special case of being dense in the
exactly. So the dense case that we have treated so far can be seen as sort of the special case where the enveloping graph is the complete graph, for which has the strongest possible expansion. It's a graph in which, for any two sets of vertices, the number of edges between them is totally determined by the size of the sets, with no error. So I want to state a version of the weak decomposition result that works for sort of objects that may not be dense themselves, but they can be embedded into dense sets. I want to give a brief, brief motivation. Actually, maybe first I'll. Right. So let's see how this kind of question arose in the proof of the Green-Tau theorem that the primes contain arbitrarily long arithmetic progressions. So guys, before their work, there were two programs to prove a statement like this. One was to see that we have Similarity's theorem that says that if we have a dense subset of the integers, then A contains arithmetic progressions. Length K arithmetic progressions. In fact, it contains a quadratic number of them, provided that n is large enough compared to delta and k. So the point is that if in this theorem we could make delta be 1 over log n, then we would get it just because a 1 over log n fraction of all the integers are prime. Although the current bounds for how large n has to be in terms of delta, so how large then can be in terms of n, are very far from allowing this kind of density. The other was in trying to argue that the primes in certain technical senses behave like a random subset of density 1 over log n. The primes in interval from 1 through n have many of the properties of a random subset of the same density. If in particular one could prove that this is true for length k progressions, then this would follow from the fact that a random set of this density has n squared over log n to the k length k arithmetic progressions. However, this is also actually this is I know this is a theorem for the sufficiently strong property that implies progressions, but was open at the time. But a lot is known about, so this is kind of a difficult question, but it is known that the almost primes of the same density. So here almost prime has to be defined quantitatively, but roughly it means integers whose prime factors are all very large, and there are very few of them. In fact, it's known how to get many twin almost primes, even though it's still hopeless to get twin primes. So the one way to look at the structure of the proof in the Green-Tao paper is that one is trying to combine those two things that we know. So the strong knowledge about almost primes behaving very much like a random subset of the integers, and the fact that we know that constant density sets do have many arithmetic progressions. So the view was sort of the following. Let's look at the integers from 1 through n. And the almost primes. So there are this relatively tiny subset. And in some sense, the entire interval 1 through n and this tiny subset behave the same. They have this strong pseudo-randomness property. Now, for an appropriate quantification, the true primes are a pretty large fraction, say a constant fraction of the almost primes. So you could wonder if this set of almost primes is indistinguishable from the entire interval, then maybe when we look at a set that is large within the almost primes, there should also be some large set of the integers from 1 through n such that m and a are indistinguishable. such as M and P are indistinguishable. Right, so I have A that looks like all the integers. I pick 1% of the elements of A. Maybe what I get looks like 1% of all the integers.
It's confusing that in Semmelweis theorem you call it set A, but you probably want to call it.
Right. So, yeah, let's go down. Now, if this model set for the primes is so large, we can apply Semmelweis theorem to it and find lots of long arithmetic progressions in M. And if the sense in which M and the prime are indistinguishable is strong enough, this will imply that also the prime must contain many long arithmetic progressions. So the general statement one is looking at is something of this form, that I have a large space, I have a possible small pseudo-random subset. I pick arbitrarily a portion of the pseudo-random subset. Is what I'm getting looking like a large set of the original set? Yeah, boss?
Indistinguishable here means what you did with the Gauss norm, this quasi.
Right, so ideally what I would like to say is that the characteristic function of M and then the characteristic function of the primes, after some scaling that takes into account the fact that they have different sizes, I would like this to be small in Gauss norm. Because that will mean that the formal expression that counts progressions in M, which I know to be a constant, will be close to the value of the formal expression for the primes. So then the primes will contain n squared times constant divided by P over M, which is log square. So they will get n squared divided by log square progressions. Actually, there's a tricky part that the generalized von Neumann theorem, the one that says that when two functions are close, the formal expression that counts progressions is close, assumes the two functions to be bounded. Well, here this function is huge. But there's a variant of the proof that works under a weaker condition that this satisfies. And then now one could use the Gauss inverse theorem to say that a sufficiently strong notion of indistinguishability is that those functions be indistinguishable by k minus one step nil sequences. This wasn't there at the time. So what I got was a really large set of functions that just by definition small inner products imply small Gauss norm.
Now it's known that the almost primes are indistinguishable from the interval 1 till n by these nil sequences.
Oh, even more was known that they were indistinguishable by this larger class of functions. No, but now I think that even that the primes themselves are indistinguishable by nil sequences is a theorem. So in particular, what's known is that the primes don't just contain arbitrary long arithmetic progressions, they contain as many as predicted if they behaved like a random set, as much as predicted by those standard conjectures on linear patterns in the primes. Okay. So let me try to state a theorem that will give this kind of will will give this kind of theorem under the assumption, which needs to be proved separately, that the almost primes do exhibit very strong pseudorandom behavior. So we'll call this a dense mode theorem because it asserts that the primes, or any set that satisfies this property of being contained in a pseudorandom set, is modeled by a very dense set. So those are also called transference theorems. Because allow to transfer things that are known about large sets to small sets that are upper bounded by pseudorandom sets. Right, so we have the same kind of setup as before. There is a, I think I'll need a big board. So my setup is the following. I'm going to be given, so I have some finite space, some collection of bounded functions, so those could also be complex valued, but let's say bounded. Those could be the nil sequences, or in other applications they could be functions computable by small circuits. And we have our function g, which now is not bounded anymore. Although there is another function which is also not bounded. So we should think of this as being the characteristic function of the primes, but scaled by the density of the almost primes. So this other function, we should think of it as being the characteristic function of the almost primes scaled by its own density. So both of them are like log n for primes for almost primes and 0 everywhere else. And they average to 1. This averages to 1, this averages to some constant. So g is less than nu, but it has some mass. Okay, I think I've got all the pieces that are given. Okay. And epsilon. All right, so we can find so we can find functions f1 through fk where k only needs to be polynomial in epsilon and delta. and a combining function such that one of the following two things is true. So one, which is really what we want, is that there is a function h which we should think of as being the characteristic function of our dense model, which is bounded dense and indistinguishable from G. Or this function nu, so the almost primes, are not pseudo-random. So this combination of the combining function and those k functions distinguishes nu from the uniform distribution. By some polynomial distinguishing. So in the case where this nu is this scaled characteristic function, this is really saying that the uniform distribution over A is distinguishable from the uniform distribution over all integers by this efficiently computable function. Or this combination of few nil sequences has this correlation with nu that doesn't have with the all one function. And for the almost primes, and for the okay, so the way this is applied in the setting is to take G to be the primes scaled, nu to be the almost prime scaled, f to be a class of functions such that this condition implies that this function has small Gauss norm. And then what remains to show is that case 2 cannot happen, because under this scaling there is no simple combination of nil sequences that correlates with nu differently than its own expectation. Okay. So So this can be proved in various ways that sort of have different advantages. One approach is to see that actually this condition that G is smaller than nu and that nu is assumed not to have, that nu is supposed to be pseudo-random for conditions of this form, is actually saying in particular that well, let's say one way to go about this is to try to get an efficient approximation for G in the sense of the weak regularity lemma. And then to see that this condition is actually much stronger than what is needed to keep that L2 squared norm under control at each step. So then this efficient approximation will be bounded and will be a function h like this. This sort of overshoots what's required by this theorem, because it not only finds a dense model for the primes, but actually a dense model which is itself described by a small number of nil sequences. Or one can go through a non-constructive proof that shows that if condition 1 is false, then that means that for every h there is an f for which this condition fails, and then apply since it's a linear condition, one can apply the Banach theorem to find essentially an f that makes all the h fail simultaneously. And that can be modified into a function that violates this randomness condition. So if I had 20 minutes instead of 2, actually that's a proof that could be given. In this other proof, the combining function is just more or less a majority. It's a very simple combination. So in fact, this is also, although the h is non-constructively defined, all the parameters are polynomially related. So if nu is pseudorandom in the cryptographic setting, where here we allow polynomial size computable circuits, and here we have negligible functions, what we get is a dense approximation which is indistinguishable in a cryptographic sense. So I'll just leave with, so without being able to describe it formally, but as an impression, one computer science application of this, which was discovered by Zembowski and Pietrank. They say, suppose we have a pseudorandom generator G as defined by Russell in his talk. So it's some function that maps m bits into n bits, where n is bigger than m. And it has the property that if we take z uniformly at random from 0, 1 to the m, and then consider the random variable g of z, this is epsilon pseudorandom for size s, where we could take s and epsilon to be something like s and 1 over epsilon to be really large in m and n. Under reasonable assumptions, this could be as large as something exponential in m. So this output distribution of the generator, even though it's very non-uniform because it has very low entropy, at least for many functions and for very small epsilon, looks pseudorandom. So we can visualize this as being, so this process where so G takes in input a short sequence of random bits and then produces in output some longer sequence. And if we compare it to a true sequence of random bits by feeding it into an efficiently computable function, at the end the expectation is going to be the same plus or minus epsilon, where epsilon is very small. Right. So the question that they posed was, well, suppose that into G we are not feeding the uniform distribution, but we are feeding a distribution where we know, or maybe we even control some of the bits. Maybe 2 bits of the input distribution are known. Now, we cannot hope anymore that the output is going to be indistinguishable from uniform. It could be that the procedure was such that this particular bit of the input always ends up here. And then now we'll always see a 0 in the first location. But you can ask, if you take away this much randomness in the input to the generator, can you actually completely destroy the pseudo-randomness? Like, could it be that by setting a few bits, you start making appear some patterns that look completely non-random in the output? So what one can prove by applying the theorem is that if here the entropy was n minus 2, because we fixed 2 bits, then here there exists some distribution of entropy at least n minus 2, which is indistinguishable from the output of the generator. Okay. So the worst that can happen is that essentially the generator is taking those bits that we fixed and throwing them into the output. So now the output has those bits fixed, and we can see them, but all the rest looks uniformly distributed. Okay. So whatever entropy deficiency is in the source of randomness for G, the same entropy, well now, of course, the output has very low entropy, but up to indistinguishability, that's the entropy deficiency that we see in the output. And so basically, the analogy is that here we can look at 0, 1 to the n as being our set of integers from 1 through n. The possible outputs of G as being like the almost primes, the pseudo-random set. The possible outputs of G after we compromise the random seed as the subset of the pseudo-random set, like the primes. And the distribution here of entropy n minus 2 as the dense model of our distribution, which was dense in the pseudo-random distribution. Okay, well, that seems like a good place to stop. Thanks. Questions? Yeah.
Is that true also if you fix n bits, that there's going to be some?
Well, okay, so in that's a good question. So in the reduction, the complexity of the reduction, which shows the distinguishability between the model and what you get implies distinguishability of the generator, you lose something which is exponential in the entropy deficiency. So if here you have m minus t bits, you lose 2 to the t in the running time. So unless your generator was exponentially secure, you cannot let this be a constant times m. And this is similar to the fact that so here, this delta, which is the density of your subset of the pseudo-random set, this is 1 over 2 to the t if t is the entropy deficiency of your generator. The complexity of the reduction is polynomial in 1 over delta, but that's as much as you can hope for. Yeah,
about the same result. What is the complexity of the reduction? Something can break, the one with the deficiency can break. What do you need to add to
the complexity of the reduction is polynomial in all the parameters, but it's exponential in the entropy deficiency.
I mean, do you need like you want to make a point before that and to take a sum or?
Oh, it's in one proof. The complexity of the combining function is a majority. Maybe it's a threshold.
So both proofs of that thing can be applied?
No, so one way of doing that proof is through iterative partitioning. Then C will have complexity exponential in K. And K will be polynomial in 1 over epsilon 1 over delta. Because you do get a polynomial number of functions that you need to combine, but the combiner is very complicated. You can do a proof by a sequential additions with truncation, and that will give you a truncated sum as complexity. Or you can do a proof using the Banach theorem, and that will be similar to Nissan's proof of the Pagliazzo-Harcourt lemma, and that will give you a majority with truncation. It will give you a sort of smoothed majority as complexity.